never have one fiber with more motor neurons. Recruitment, this is multiple motor units summation. Now, summation, we would get the sum when we added. This is adding. It's recruiting more, adding more. In a whole muscle group or a group of muscles, smooth motion and increasing tension are produced by slowly increasing the size or number of the motor units stimulated. When all the motor units are reaching tetanus, it can only be sustained for a very short time. This is maximum tension. A person cannot, a muscle cannot maintain maximum tension over a long period of time. Here you can see the spinal cord, and this is the size of a dime in real life across the spinal cord. You can see the somas, the cell bodies, and the axon coming, the motor neuron, coming from the spinal cord to innervate maybe hundreds of muscle fibers, each one. But never will one of these muscle fibers be attached to more than one neuron. Does not happen. Sustained tension. This is not maximum tension, but less. And it allows the muscle units to rest in rotation. So I'm holding up this glass full of whatever it might be. I can hold this glass over a longer period of time because they're going to rest in rotation. Those motor units will rest in rotation. Muscle tone. This is the normal tension and firmness of a muscle at rest. The muscle units are going to actively maintain body position. If you think of a bodybuilder, they've increased muscle tone. Their muscles become really rather firm, very hard or firm. This is going to increase the metabolic energy used even when that bodybuilder is asleep. They're using more energy even at rest. So there are two types of contractions. There are isotonic contractions and isometric contractions. The isotonic contractions, these change the length of the muscle. Maybe the muscle is going to shorten and maybe it'll lengthen. But isotonic contractions change the length, and this results in motion, changes the length of the muscle. Iso means same, and metric means measure. Isometric, these are the same measure. Even when the tension is building, there's no change in the length of the muscle. So if we put our hand up under the table in front of us and lift as much as we can, we're lifting, but the table doesn't come up. So the muscle is developing tension, but it's prevented from changing length. Isometric. The heavier the load, or the heavier the resistance on a muscle, the longer it takes for shortening to begin. And the less the muscle will shorten. So you could practice this if you go around your house and find things that are heavy that you can lift up, and things that are not so heavy, some things that are light, and see how long it takes for you to lift that item and how much the shortening is. Can you tell a difference with the muscle shortening or not? Can you tell a difference with it taking longer because it's heavier? Muscle relaxation, return to resting length. The elastic forces, the pull of those elastic elements, the tendons and ligaments, these are going to expand the sarcomeres back to their resting length. Oppositional muscle contraction, these reverse the direction of original motion. We have opposing skeletal muscle pairs. We also have muscles that work synergistically with the prime mover, which is the muscle, like if you're lifting up a weight and you'll use your biceps brachii, that's the prime mover, but they're going to be oppositional muscles, and they're going to be muscles that work synergistically with that biceps brachii. And those we have to have for control so we don't move spastically. Gravity can take the place of an opposing muscle to return it to its resting state. Now we're on slide 42, and we're going to have about 55 or 56 in this set. A person's attention span is about as many minutes long as they are years old, years of age. You can always pause these and come back and listen again. We're going to start on another topic here, 10.6, another topic in the chapter. We're going to talk about ATP, adenosine triphosphate. And so I put a little diagram in the upper right-hand corner here so you can see the adenosine and the sugar and then the 3 phosphates and how these have a little bit of energy that hold those parts together. And you can see how the most of the energy is between the 2nd and the 3rd phosphate. And when your body needs that energy, that 3rd phosphate is released and the energy is captured to use for metabolic purposes. Then our adenosine triphosphate has become adenosine diphosphate. The body's going to take those parts and recycle them and make ATP again. ATP provides energy for muscle contraction. Sustained contraction uses a lot of ATP energy, and the muscles, they store enough energy to start a contraction, but the fibers are going to need to manufacture more ATP as it's needed. ATP and ADP, these are recycled continually. Creatine phosphate, CP, creatine phosphate, this is the storage molecule for excess ATP energy in a resting muscle. You want to know what creatine phosphate is. Everybody knows what it is. Energy recharges ADP to ATP. It's recycled, and it's going to use the enzyme creatine kinase, CK, to do that. So you want to know what creatine kinase is also. If you see any word that has to do with anatomy and it ends in ASE, typically it's an enzyme. If it ends in ASE, it's usually an enzyme. If it ends in OSE, a lot of time it's a sugar. But the ASE ending, it typically is an enzyme. When the CP is used up, other mechanisms generate ATP. So let's differentiate between aerobic and anaerobic. Aerobic metabolism, fatty acids in the mitochondria are broken down into fatty acids. They break down the fatty acids, and this is going to make 34 ATP molecules per glucose molecule. And I had this all plotted out in various sizes of beads, making molecules all over a wall one time. You take the glucose molecule and it will produce 34 ATP in the aerobic metabolism, creating energy. Aerobic is with oxygen. Anaerobic, there's no oxygen available. Anaerobic glycolysis, this happens in the cytoplasm. It's the primary energy source for peak muscular activity. Peak muscular activity. Anaerobic glycolysis, this is the primary energy source. Only 2 ATP molecules are going to be created out of each molecule of glucose. This is breaking down the glucose from the glycogen stored in the skeletal muscles. aerobic with air, 34 ATP molecules per glucose molecule, and this happens in the mitochondria. Anaerobic, this is going to happen in the cytoplasm. It's during high peak muscular activity, and 2 ATP molecules are going to be produced for each molecule of glucose. A drastic difference. They're used at different times, and you probably want to remember those. When skeletal muscles are resting, they metabolize fatty acids. They store glycogen. During light activity, muscles are going to generate ATP through the anaerobic breakdown of carbohydrates, lipids, and amino acids. At peak activity, the energy is provided by anaerobic reactions, and that's where lactic acid comes from. It's a byproduct. Lactic acid buildup will cause a person to feel very sore after they've been working out quite a lot. The body can make energy out of carbohydrate, fat, and protein. The body cannot build tissue when it needs protein. It can't build it out of carbs and fats, only from proteins. Just an aside. What is muscle fatigue? Well, that's when they cannot work anymore. They can't function like they need to anymore. Why does this happen? Maybe the metabolic reserves are depleted. They're gone. Maybe the sarcolemma and the sarcoplasmic reticulum have been damaged. The lactic acid buildup may have caused too low of a pH. And the result is going to be muscle exhaustion and pain, along with the inability to perform the required activity. Muscle fatigue. The recovery period. This is the time that's required to recover, for the muscles to return to normal after exertion. The oxygen is going to be available like normal, homeostasis, and the mitochondrial activity is going to resume. The Cori cycle, this is the removal and recycling of the lactic acid. The liver is going to do that. The liver will convert lactate to pyruvate. The glucose is released, and this will recharge the muscle glycogen reserves. So the body's recycling everything. When something's completely and totally worn out and unusable again, it will be excreted. Oxygen debt, this is after exercise or exertion, and the body needs more oxygen than it can, than it usually does to be able to normalize its activities. The person's going to breathe very, very heavy. Not excess, a lot of heavy breathing to replace that oxygen debt. It's not really an excess because the body actually really needs it, but it's called excess post-exercise oxygen consumption, EPOC, EPOC. Oxygen debt. Heat production and loss. The muscles produce heat, and about 70% of that can be lost as heat. If you are getting around in the morning, it's wintertime and it feels kind of cold, and you move around a little while and you're thinking, wow, it's not cold, it's just fine. Your body has built up that heat. Your muscles moving by you, quote unquote, getting around or moving around, created more heat. It raised your body temperature, and then you're comfortable, or maybe overwarm here in Arizona. Hormones and muscle metabolism. Moving around is going to create heat, but hormones, they affect every aspect of our entire body. Growth hormone directly affects muscle growth, muscle formation. Testosterone directly affects muscles. Sometimes a man will take testosterone injections to try to prevent muscle loss or to try to rebuild some muscle that has been lost. Testosterone helps build muscles. Men typically can bulk up more than women can. There are women bodybuilders and they do bulk up, but typically they cannot bulk up like a man can unless there's something going on with the hormones there. Thyroid hormones, thyroid regulates absolutely everything about your metabolism. And the thyroids directly affect your muscle maintenance, muscle growth, and every other system. Epinephrine, get that shot of epinephrine, feel good, and get where you can actually, it affects your muscles. Muscle performance. We have force and endurance. Force is the maximum amount of tension produced. What can your muscle produce as far as tension goes? That's the force. How long can it keep that activity up? How long can it be sustained? This is endurance. Force and endurance. These depend on the types of the muscle fibers and the physical conditioning. A person in great physical conditioning, someone with well-developed muscles, they're going to have better force and better endurance. Another way we're going to categorize muscle, we have skeletal muscle, we have fast fibers, slow fibers, pardon me, and intermediate fibers. Fast fibers, just like their name, they contract quickly. They have a large diameter, large glycogen reserves, few mitochondria, strong contractions, but they fatigue quickly. Fast fibers, they're fast, effective, and they stop fast as well. Fast on, fast off, and they're effective when they're on. Slow fibers are the opposite. They're slow to contract, slow to fatigue. They have a small diameter, more mitochondria, a high oxygen supply, and they have myoglobin, which is a red pigment that binds oxygen. Slow fibers are slow to contract and slow to fatigue. Thinner fibers. The intermediate fibers, those are just in the middle, intermediate between the fast and the slow fibers. Hypertrophy and atrophy. Hyper, excess, more, a lot. Trophy, hypertrophy. These are going to be large muscles from heavy weight training. The diameter of the muscle fibers is increased, the number of myofibrils is increased, and the mitochondria and glycogen reserves are increased. Hypertrophy, think of the Incredible Hulk. This is a bulked up hypertrophy. Muscle atrophy, think of someone small in a wheelchair or bedridden. They don't have much muscle activity. The muscles are smaller. They're flaccid. They do not have good tone. They don't have as much power. So if you take an elderly person, a 90-year-old that I know who fell down night before last, it's not bone loss, but it's a lack of power, a lack of strength. The muscle units don't have power. There's not strength. There's not tone. And the size has dwindled and become smaller. That's the end of skeletal tissue. We only have a few slides left, 5 or 6. 5 slides remain, and we'll be covering both cardiac muscle and smooth muscle. And they're covered less here in this chapter because we're going to cover them again in chapters down the road, so to speak, later chapters. The cardiovascular chapter will talk about cardiac muscle tissue again, along with the vessels. The cardiac muscle cells are striated. That's the same as the skeletal muscle. They're both striated. The only muscle not striated is smooth. The cardiac muscles are only found in the heart, nowhere else in the body. The striations are like the skeletal muscle striations, and this is because of how the muscles are arranged. The myofilaments, they're smaller. So cardiac muscles, they are small. They have one single nucleus. They have short, wide T-tubules. They are aerobic. They're high in myoglobin and mitochondria. They have intercalated disc. Cardiac muscle tissue is the only tissue with intercalated disc. Those intercalated discs, they join the cell membranes. So the adjacent cardiocytes, the gap junction, so to speak, these are intercalated discs. They help maintain the structure. They enhance the molecular and electrical connections, so they conduct action potentials. So they physically help the heart maintain its structure. They also help conduct electrical impulses through the heart muscles. They help coordinate cardiocytes. They link the cells mechanically, chemically, and electrically. The heart then functions like a single fused mass of cells. And we'll talk about that more when we get to the circulatory system. You can see the heart has intercalated discs. Pardon me, these little discs here. And that's the only tissue that has the intercalated discs. Heart tissue contracts without neural stimulation. There is neural stimulation, but the actual heart cells will contract without outside stimulation. If you have cardiac cells in a petri dish, they're all going to beat. And if you give them a little bit of time, then they're all going to beat together in unison. That's their nature. That's how they are. That's how they function. These are controlled by pacemaker cells. The contraction, controlled by pacemaker cells. And then that variable contraction tension, this is controlled by the nervous system. There's an extended contraction time. They contract 10 times as long as skeletal muscle. Also, there's a longer refractory period, and it's the space between the contractions. It's the rest in between. They have a very long refractory period, and this maintains regular cardiac contractions. There's no, it prevents that potential from going backward and it becoming chaotic. And we'll talk about that more when we get to the circulatory system. Smooth muscle is our last type of muscle to talk about. It is pretty much all over the body. It's going to form around other tissues. In the integumentary system, I put a little image here. You can see a hair follicle where an erector pili muscle is attached at the base. When a person gets goosebumps, it's because this erector pili muscle has shortened, and it causes that little dimple on the top of the skin. This is smooth muscle. Also, smooth muscle is in the blood vessels and the airways. When the blood vessel smooth muscle constricts, the blood pressure will raise. It will go higher. That is not the only aspect of maintaining blood pressure, though. That's only one aspect. The reproductive and glandular systems, the smooth muscle produces movements. So in the outer third of that oviduct or fallopian tube, that's where the egg is to be fertilized. That egg, that fertilized egg, needs to be moved over into the uterus so it can implant appropriately. Smooth muscle is what does that. The glands need to secrete, and the smooth muscle helps that happen as well. In the digestive and urinary systems, the digestive system, for example, the intestines, through peristalsis, that smooth muscle pushes and pushes and makes that material go clear until it gets to the anus, that sphincter at the terminal end of the digestive system. And that smooth muscle regulates the material going through the intestine and elimination as well. Urinary system, we have two sphincters in the urinary system, one voluntary and one involuntary. We'll talk about those when we get to those systems. Structural characteristics of smooth muscle tissue. Well, it is non-striated. The other muscle is all striated. Smooth is not. It's the only one that's not striated. It has a different internal organization. The actin and the myosin are there, but they're put together differently. Smooth muscle cells are long, slender, spindle-shaped. They have a single central nucleus. There is no T-tubule, no place to put them. There's none necessary. No myofibrils or sarcomeres. They have no tendons or aponeuroses. There's no use for them. They have scattered myosin fibers, and the myosin fibers have more heads per thick filament in the smooth muscle. The thin filaments are attached to dense bodies. You can see a little dense body right here and here and here. And the dense bodies transmit the contractions from cell to cell. So each of those dense bodies make that impulse go farther to make that good contractile tissue. And that is the end of Chapter 10, Smooth and Cardiac and Skeletal Muscle Tissues. Feel free to review, to put it on while you're washing dishes or doing something else, and you will have the familiarity with each of these terms and maybe help a little bit with memory of some of these lists, how the terms go together, how the physiology works with various types of muscle tissue. I will also make an outline now and provide some review sources, and I'll put those into Canvas for you. And this is the end of Chapter 10. Chapter 11, we're going to begin with the actual muscle organs. So have a beautiful evening. Have a good night. Thank you for your questions, and we'll meet together again tomorrow night.